Okay, welcome back. Let's move on to the practical overview of estimation and confidence intervals. In this video, I'll kind of give some important background information prior to diving into two different examples. And the background information that I will provide you is background information for the three steps in the process of estimation. Right, there are these three steps that we'll follow when we estimate a population mean using point estimation and interval estimation. And so the first step is to compute the sample mean and the standard error. And as you can see here, I have some different symbols for sample error, which we'll go over, or for sample error, for standard error, which we'll go over in this video. Step two is to choose a level of confidence and find the critical values at that level of confidence. And then step three is to compute the estimation formula to find the confidence limits. And so we'll walk through these one by one. Again, first I'd like to provide some important background info for each step before we do examples where we actually walk through all three at once. And so first, step one, computing the sample mean and standard error. For starters, okay, the sample mean, I think we're all familiar with that at this point, so I'm not going to spend time on that, but I would like to spend time on the standard error. And so first, in terms of why we use standard error in this process of estimation. Well, let's think back to the last module when we talked about sampling distributions and we learned about standard error. What is that? And I'd really encourage you to pause the video and go back to your notes, try to think this through, just try to find the answer yourself, either from memory or ideally from memory, and then whatever you can't get, go back to your notes and try to find the answer there. So I'll give you a second to pause if you'd like. Okay, and I'm going to assume at this point that you'd like me to proceed. And so standard error is the standard deviation of the sampling distribution of sample means. And so I drew this out. It was hard. It's really hard to find graphics, so I apologize that you have to see my chicken scratch. But so you can see here, this is a population, this red distribution up here. And you can see these smaller ones in pencil. These represent samples of size n. And then together, these samples, essentially you can aggregate to or approximate to the population mean in the sampling distribution, right? So this is the sampling distribution of sample means. And then the standard deviation of the sampling distribution is standard error, right? And so you can see that, what is that, sigma m, right? You can see that at each of these various lines here. So this is mu plus 1 standard error, mu x plus 2 standard error, right? And so again, the standard error represents the standard deviation of the sampling distribution down below the population distribution. And so this was the formula that you previously were exposed to. So you can see here, standard error of the mean equals the variance divided by the sample size, or rather the square root of the variance divided by the sample size. We can reduce that to the standard deviation divided by the square root of the sample size. Wow, I'm sorry, I'm stumbling over my words in this video. I'm recording this at night. And so to go back to this, if we are considering the standard error as a standard deviation of the sampling distribution, then if we do plus and minus one standard error in this sampling distribution, per the rules of normal distributions that we've gone over previously, that represents 68% of the area under that curve. Or in other words, 68% of all possible sample means fall within the first standard error of the mean in a sampling distribution. So in other words, even more simple terms, we can say with 68% confidence that the population mean falls within this interval in any given sampling distribution, right? So if we calculate a sampling distribution using sample statistics, then we can generally say with 68% confidence that the population mean falls within this interval, plus or minus one standard error of the mean, right? And so that's the reason we use standard error, is because that all comes back to, again, using these sampling distributions to inform the inferences that we draw from this. In this case, the confidence intervals for the population mean. And this model, since we're talking about estimation. right? So that's a little bit of background of why we use standard error. So to give a very simple example for that, suppose we selected a sample of 100 participants and we found a sample mean of 4 and a standard deviation of 5. So then here, going back to the previous video, the point estimate is 4, right? The sample mean is our point estimate of the population mean. And then if we substitute in the standard deviation and the sample size into that formula for standard error, we'll see this, right? So the standard error represents the standard deviation divided by the square root of the sample size. So standard deviation was 5, plug that in. Sample size was 100, plug that in. That will reduce to 10, so this will be 5 over 10 equals 0.5, right? Our standard error is 0.5. And so then if we just add and subtract that one standard deviation, that one standard deviation, or more accurately, that one standard error from the sample mean, we'll acquire that interval, right? So in this graphic, 4 was our sample mean, plus 0.5 plus 1 standard error is 4.5. 4 minus 1 standard error is 3.5. Then we can say that at least 68% of all possible sample means fall within 1 standard error of the sample mean, right? So that's, again, just one example of why we use the standard error to help us calculate these confidence intervals. And you might notice here, if you have a keen eye, you might notice that the formula for standard error here looks different than what I just showed you on the previous slide. So why is that? Right, previously we had, what was that, sigma here, and now we have, oh gosh, it's not sigma, what is that? I need to look this up. All right, I paused it and looked it up, and it is sigma, all right? Man, Greek and statistics is confusing. Anyway, in previous equation or formula, you saw that it was sigma, and here again was sigma, and now we have S and SD. So why is this different? Well, let's talk about that. So in the last module, we talked about the standard normal transformation, standard normal distribution, z-scores, right? All this stuff that should hopefully be reviewed at this point. And in that, we were using the standard normal transformation as a formula to convert any normal distribution to a standard normal distribution. In other words, we're using that to convert any distribution to a standard normal distribution with a mean of 0 and a standard deviation of 1, right? And so that was helping us to essentially calculate z-scores, right? Because z represents those standard deviations in the standard normal distribution. However, to calculate z, right, to calculate that formula, we have to know population variance. And in reality, that's rare in social science. In our next module, we'll learn more about z-scores and hypothesis testing. Again, there are some terms I'm kind of throwing at you in this module that you're not going to have a full body of background knowledge of, and that's okay. So just know that we'll talk more about z-scores in the next module and talk about how we use them for hypothesis testing. But for this module, again, just reminding us that they exist and that to calculate them and to essentially to use z, we have to have already known the population variance, and that's not often the case in social science research. And so if we know sample variance, right, because we can virtually always calculate that if we've collected a sample. So if we know sample variance, but we don't know population variance, we can calculate t instead of z. And again, getting a little bit of ahead of ourselves, this is something we'll come back to. But t-tests use estimated standard error instead of standard error. And so estimated standard error is just that, right? It's an estimate of the standard deviation of a sampling distribution. And so if, again, going back to this formula, if this is standard error of the mean, when we know the population variance, right, because that's this right here, the numerator in this fraction, estimated standard error of the mean, it's the same, just slightly different notation, right? So now it's S sub m, and rather than variance, we just have our sample variance instead of population variance. So in other words, we have standard deviation instead of population standard deviation. Right, these are sample statistics, these are population statistics, right? And so again, in our next two modules, we'll learn more about using t-scores and hypothesis testing. You might have heard of t-scores before, or t-tests. Maybe you've even done them in other classes, but if not, or even if you have, don't sweat it for now. We'll come back to it. But again, I'd like to start introducing us to these terms and hopefully make them a little bit less scary. And to know that in t-test, that's when we're using estimated standard error because we don't know the population variance, right? That's really the only key distinction for this module. And so I made a simple flowchart for you to help with that. So in this module, if we are stumped or if we need to review, just ask yourselves, okay, is population variance known? Have we been provided either of these statistics, the variance or population variance or the population standard deviation? If the answer is yes, that's great. We can do z-scores and we're going to use standard error. If not, that's okay. We'll use t-scores and estimated standard error. Right, so that's some background information for step 1. For step 2, choosing the level of confidence and finding the critical values of that level of confidence. So as we just mentioned, we use standard error because it helps us estimate the value of the population mean. Right, again, like here we said that, oh gosh, what just happened? Sorry, my scroller on my mouse is very sensitive. It's new and I'm still getting used to it. So again, here in this sampling distribution, plus or minus 1 standard error of the mean, we said that 68% of all sample means fall in that area. That one's easy, right, if we're looking at plus or minus 1 standard error of the mean. But some levels of confidence don't overlap neatly with standard deviations, right? So for example, here's the general percentages or values of the area under the curve that fall within these standard deviations. But if we look at this and pull it over, we can see this doesn't overlap neatly, right? This is kind of in between those two lines. And this is a 90% level of confidence here. Right, so it's 90% is represented in the blue. Then that's 5% over here, 5% over here, because together they add up to the remaining 10%. And then Z is essentially this value, right? So it looks like 1.6-ish, right? 1.7-ish, somewhere around there. But again, it doesn't overlap neatly with this. It's not going to be a whole number like in our previous examples. And so I'd like to pause at this point to talk about the fact that there are going to be different types of distributions that we see in this course, 1 and 2 tail distributions. And so when we hear the term tail, that just refers to how many critical regions are included in the test. So here, this is an example of a 2-tailed test, right? Because we have 2 critical regions, right? And critical regions essentially just think like the thing that we're interested in, right? What's critical? What are we highlighting? Where is the probabilities coming into play? Right, so in this case, it's a 2-tailed distribution. And again, we'll come back to this, but I want to start getting us familiar with this, making it a little bit more comfortable. And so a 1-tailed distribution might look like this, right? So here it's still 5% on the right side, except here there's no left tail, right? We're just looking at that 95% that is less than whatever this value is. It's like z-score or whatever it may be. And we could also have a 1-tailed distribution that looks like this, right? So we just essentially flip it around. Right, so again, introducing us to this in the modules or rather in the content in this module, we're primarily interested in 2-tailed distributions because we're looking at confidence intervals, right? So values plus and minus the mean, right? And so we won't really come across 1-tailed distributions in this module, but wanted to introduce you to the concept. And so going back to this then, if we're looking at 2-tailed distributions, how do we determine z-scores when we're calculating those confidence intervals? Right. Well, if we look back at this, at the unit normal table, these are slides from the past module. Let's zoom in on this here. You can see column C was the area beyond the tail, area beyond Z in the tail, with Z representing, in this case, this value here. Then essentially we just need to keep in mind, or be mindful of what we're looking for in column C, right? To recognize that although this is showing it as one side of a distribution, we need to be thinking of the full distribution as we calculate it, right? And so to explain what I mean there, if we're looking at like this 90% confidence interval, to determine the z-scores, well, to basically, in other words, to know what we need to look up in column C, we can take 100% minus the level of confidence divided by 2. So here, that's if we're looking at a 95% confidence interval, 100% minus 90%. is 10%, right? Again, that's what's left outside of the 90%. Divide that by 2, that's 5% or 0.05, right? And so that's representing this. And so that's what we need to look up in the Z table, right? And so if we do that here, we see that 0.05 in column C falls between these two. It falls exactly between these two. This is 0.0505, this is 0.0495. And since it falls between those two, we need to take the average of the two z-scores. Z-scores here are 1.64 and 1.65. So we add those two up, divide them by 2, and we get a value of 1.645. Right, so that's how we determine z-scores when calculating confidence intervals. Again, basically just we need to be mindful of the whole distribution and recognize that this table is telling us the story of 1/2 of that distribution, which is why we divide by 2 here. Yeah, so that z of 1.645, bam, right there. And so this would be, what would this be? Think to yourself, it'd be minus 1.645, essentially, right? It might not be reflected in this table, but it's just the negative inverse of that. Okay, so that's that background information. I promise we're almost there. So step 3, computing the estimation formula to find the confidence limits. Here are the estimation formulas for you. Again, big scary things that you're not familiar with, like what is a 2 independent sample t-test? That's scary. Well, don't worry, we're not going to cover that in this one. In this module, we're focused on these two. When we say one sample, that means exactly what it sounds like. We're just looking at one sample in particular, and Z or T. And again, if we need to determine if we should use Z or T, just look at that flow chart I provided for you. Do we know population variance or not? And that will tell us what we need to do. And here are the estimation formulas then for these two. And so in the T distribution, right, or if we're looking at one sample t-tests and we're estimating for those, then we'll need to look at a new table. And so this is the T table. This is in Appendix C right after the Z table. And again, this one might look scary, but I promise it's approachable. We'll figure it out. This is what we'll use to look at probabilities and critical values in a T distribution. And so here we need to know a few things. First is degrees of freedom. That term we'll define in the next few modules. For now, just know that we can give this by knowing n. Degrees of freedom here is just n minus 1. So if our n is 10, degrees of freedom is going to be 9. Right, it's straightforward. We also need to know the number of tails and proportion of tails, or proportion in the tails, right? So again, like we talked about, 1 and 2 tails, those are some examples of distributions we might see. So let's just do a couple of examples here. Again, most of what you'll see in this module is 2-tail distributions, but I'd like to give you examples of both to help you understand or distinguish between the two. So in a 1-tail example, if I'm asking you to find the critical value of t when n equals 6, then the proportion in 1 tail is 0.025. In other words, this here is 2.5% of the overall distribution. So we need to find, oh yeah, and 2.5%. Here we see proportion 1 tail 0.025. Okay, it's telling us that we're looking in this column here. Degrees of freedom is n minus 1 equals 6 minus 1, right? Because that was our n equals 5. There's our 5. And then we just look at those two columns. And we're going to find a critical value of t of 2.571. Right? So that's an example of finding the critical value of t in a 1-tail example. And a 2-tail example, what you'll see in this module, let's say we need to find a critical value of t when n equals 10, and the proportion at 2 tails equals 0.02. Right, so 0.02, that means that this is 1% and this is 1%, right? 100%. Yeah, I don't need to do the math for you. Yeah, this is 98%, this is 1%, this is 1%, that's 100% altogether. And to do the degrees of freedom, n minus 1, what is that going to be? You can do the math yourself. It's going to be 9. And then we just look at those two columns. We're going to find a critical value of t of 2.821, right? And that's what we see here, right? And so then this is going to be this value of t would be minus 2.821 if we wanted to calculate it or label it, but we don't need to, right? Generally, we just need to find that one value of t. Okay, so let's do some examples to consolidate all that together and wrap up the videos here. So example 7.1. So let's estimate some population means. Cool. So IQ scores in the general healthy population are approximately normally distributed at 100 plus or minus 15, mu plus or minus sigma. And so let's say we collected data from a sample of 100 students, and we find a sample IQ of 103, right? So our M equal 103. And let's say we're just doing tests here, and we're trying to see if the IQ of graduate students is different from that of the general population. And so what I want you to do is, using that sample mean, I want you to find the 90% confidence interval for these data. In other words, ignoring what's previously known. Oops, sorry. Ignoring what's previously known, right? We want to take this sample mean and find the 90% confidence interval for the population mean. And so first, let's review the flow chart to see which test we need to use. Okay, so is population variance known? Pause it and think to yourself. What you should find is that the answer is yes, it is known. Therefore, we should use z-scores and standard error, specifically, right, because we can see population, in this case, population standard deviation is right here. Okay, so now we know that we're using a z-test, and again, in this module, we're just focused on one sample test, so this is a one sample z-test. So step 1 is to compute the sample mean and standard error. Step 2 and step 3, right, previously, the steps that we saw previously in this module, in these slides. Okay, so let's start with step 1. Compute the sample mean and standard error. Well, this is easy. Sample mean is 103 because it's provided right there for us. Standard error, okay, in this case, we're going to calculate sigma, right, because we know population variance and population standard deviation. And what was it? Standard error of the mean equals sigma divided by radical n. What is n here? Think to yourself. Ding, 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 100. Right, so 15 divided by radical 100. 15 divided by 10 is 1.5. So there you have it. We calculated the mean and the standard error. Step 2, choose a level of confidence to find the critical values at that level of confidence. So here, we don't need to choose. It's been stipulated for us, 90% confidence interval. So in other words, we're looking for 90% of sample means that surround the sample mean of 103. Right, so in other words, if this is 103, right, this right here in the middle of this, we're looking for the 90% of means that surround that. Therefore, we'll have 5% on the tails. And so that equates to 45% above and below the mean, or 5% remaining in each tail. Right. Yeah, and so this one directly relates to the previous example of how we use the z-table in these estimation, or when we're using confidence intervals. And so we'll look up column C in our table of 0.05 or 5%, and we'll find a z of 1.645. Okay, so that's the first little bit here. So now step 3, compute the estimation formula to find the confidence limits. Well, you can go back to the table that was earlier in these slides, and you'll find that the estimation formula is m plus or minus z times standard error. And so first, let's just calculate that second part of the formula, z times standard error. So z, we just got on the previous slide, we found that it was 1.645. Standard error here, we calculated as 1.5, so we just multiply those together and we get a value of 2.47. And so now let's calculate the upper confidence limit. In other words, now we're not looking at a z distribution, so this looks different, the values here, than on the previous slide. So now we're saying that, okay, our sample mean was 103. What's the upper confidence limit, right? What is this value that represents the upper confidence limit for these 90% of sample means surrounding 103? And so it's going to be the m plus z times standard error. So in other words, our mean plus 2.47, right? We're calculating this value right here. And we do that, 103 plus 2.47 equals 105.47, right? We identified that value. Now let's do the exact opposite for the lower confidence limit. I encourage you to pause it here and try to do this yourself. And what you'll do is our mean minus 2.47, right, to calculate this. And very intuitively is 100.53. And so all that told, basically what we find here, one interpretation, is that at 90% confidence interval, the tree population mean IQ score falls between 100.53 and 105.47 in this population of students. Right. So in other words, again, we're not hypothesis testing. We're just drawing conclusions here via estimation. Right. We're not making informed decisions about our null hypotheses and whatnot. But here, this seems to suggest that the population mean is actually different than what we reported up here, what we were told, right? Because that value, 100, falls outside of this 90% confidence interval, right? To be further down here. Or another way to phrase that is that we are 90%. Oh my God, I'm sorry, this wheel. I'm still getting used to this mouse. I just bought it a few days ago. In other words, what we're saying is that we are 90% confident that the population mean IQ score falls between 100.53 and 105.47. Right, so a few steps. Hopefully this gets more intuitive. But a few steps that kind of are starting to tell us some interesting things about our data. So one more example here. So in 2007, Albert et al. Studied relatives of patients with obsessive compulsive disorder, or OCD. And their sample size was 18. And they measured the social functioning of relatives using this 36-item survey. And the scores on that survey ranged from 0, which represented the worst possible social functioning, to 100, which represented the best possible social functioning, the best possible health. So 0 is very poor health, 100 is very good health. And they found a sample mean of 62 and a sample standard deviation of 20.94. And I want you to find the 95% confidence interval for these data. So again, let's review the flow chart. Do we know population variance here? Let's go back. Sure doesn't seem like it, right? Or it's not given to us. So we're going to say no. So then we must be using t-scores and estimated standard error. So we see our steps here, what we've seen before. Now we're using estimated standard error, but beyond that, the steps are generally the same as what we just did in example 7.1. So step 1, compute the sample mean and estimated standard error. Sample mean we already reported to 62, right? It's right there on the gray on the left. Standard error, right? That's going to be standard deviation divided by the square root of n. So 20.94, this value divided by 18, our n, and we're going to get a value of 4.94 when we do that math. So that's easy. Step 1 is done. Step 2, choose the level of confidence, find the critical values at that level of confidence. What's the level of confidence here? It's 95. Right, in other words, we're looking for 95% of sample means. It's around the sample mean of 62. Yeah, and so here actually, I guess this one looks a little off. This should be, or no, I guess at this point, if we're thinking about our t statistic, so in a t distribution then, we're looking for 95%, right, these values. So we need to find what t is on this t distribution. And so if we look at our t table, table C.2 in your textbook, the proportion in the two tails combined is 0.05. In other words, 2.5% over here, 2.5% over here. That means there's 5% total area outside of this interval. So we look at 0.05. That's a proportion of two tails combined. And what's our degrees of freedom? We'll need that for the table. It's going to be n minus 1, or it's going to be 17. And so if you look that up in the table, you'll find a critical value of t of 2.110. Right, so that's what it looks like in a t distribution. Now let's go back to our sampling distribution and create that. So compute the estimation formula to find the confidence limits. Again, if we have our distribution here, we're calculating m plus or minus, in this case, t times standard error. So multiply t by the standard error. Let's do that first. We just calculated our t of 2.110. In step 1, we calculated the standard error at 4.94. We multiply those together, we get a value of 10.42. Right, and so again, if this is our sampling distribution, all right, 62 right here is our point estimate. Let's calculate the upper confidence limit, our mean plus this value. 62 plus 10.42 is 72.42. And then we'll calculate the other side, the lower confidence limit. What is our mean minus 10.42? Well, the answer is 51.58. Right? That's all there is to it, right? It's that simple. And so here we can say we are 95% confident that the population mean falls within the range of 51.58 to 72.42. Or in other words, the 95% confidence interval in this population is a score between 51.58 and 72.42. Right, so a couple of basic examples here of how we can use estimation to draw some inferences or learn something about our population mean without necessarily having to make the formal decisions that we'll have to in hypothesis testing. We'll move on to hypothesis testing in the next few modules. And along the way, we'll also revisit estimation, especially for some of the more complicated t-tests that we didn't get to in this module. But that's all for now. Good luck with everything, and we'll see you next time.